All right, here we're going to look at Hamilton circuits. A Hamilton circuit, you start and end at the same vertex and visit each vertex exactly one time. Now this graph is a complete graph. Definition of a complete graph: there's a direct edge between each pair of vertices. Every pair of vertices. Okay. A direct edge between every pair of vertices, and that's what's going on here. Now, what I want to do is I want to make a Hamilton circuit through this network, which means I have to start and end here at A and visit every vertex exactly once. And there are many different ways I could do that. Just show you a couple of possibilities here. I could go from A down to B, B down to C, C over to D, D over to E, and back to A. That'd be one way. Another way I could do it I could go from A to C, from C up to E, E over to B, B down to D, and then back up to A. Right? Now, if you think about it a little bit, you'll recognize, well, wait a minute, there might be quite a few different ways that I could make that route. And in truth, there actually are quite a few different ways. In this case, the order is, let's call it n equal 5. If you remember how we defined order, that's the number of vertices in the graph. Turns out that the number of Hamilton circuits in a graph that's complete of order n, right? So this is a complete graph. Remember that there's a direct graph between every pair of vertices. The number of Hamilton circuits in a complete graph of order n can be found using this formula: n minus 1 factorial divided by 2. Now in our example, it'd be 5 minus 1 factorial divided by 2, or 4 factorial divided by 2. Now if you have never seen this symbol factorial before, don't be scared of it. It's pretty simple. 4 factorial means you just start at 4 and you count your way down all the way to 1, and then you multiply those numbers together. So 4 times 3 is 12, times 2 is 24, divided by 2 is equal to 12. Right, so in fact, in this case, if I wanted to draw all the different Hamilton circuits, there would be 12 of them. I've shown you 2 of them. If you have some time, you might want to try and see if you can come up with the other 10 on your own. Now, it turns out that if I were to take a look at all possible circuits that are Hamilton circuits in this case, there would actually be twice this number, 24. But when we use this formula, we don't want to count the same root in reverse. So if I were to look at A, B, C, D, E, and A, that's exactly the same root as going from A to E to D to C to B to A. So this number doesn't count those as 2 different ones. It counts the direction here, and the direction back is just 1. So you'll find 12 different roots. Right? And that's a good review or a good introduction to Hamilton circuits. Remember, Hamilton circuits, you start and end at the same spot. You visit each vertex exactly once, and then you come back to the same vertex. If you have a complete graph of order n, order is the number of vertices, the number of Hamilton circuits in your graph is n minus 1 factorial divided by 2. And we did the example here. We came up with 12.